Yeah. So, yeah, calculus. How things change, right? So there's basically two aspects of it, right? Taking derivatives and taking integrals, and they're kind of inverses of each other in some way. So we'll start with derivatives. Yeah, that might be legible. So the derivative is how the function changes as you change the variable, right? So if I have just some generic function f that's a function of x, and I have, so it has a curve like that, then if I say, okay, the value at some x1 is this, and the value of some x2 is that, right? So here's f of x1, here's f of x2. Basically, the derivative of x, so f prime of x, which is, you could write that as df dx, is f of x2 minus f of x1 divided by how far x2 is from x1. As these get close. Right, so that's a very casual way of defining derivatives. In math, you'd say like it's this distance as you take the limit as this goes to 0. Right. So, well, what is that? It's basically rise over run. Right. If you learn that terminology for finding slope of a straight line. Right, so if these are far apart, now that's not quite a straight line, but it's close to a straight line. And as I bring them closer and closer together, it gets straighter and straighter. Right, so that's kind of what this is built off of. Now in math, you got to do all sorts of other things because this could be discontinuous or it could be some gross thing. In physics, we don't have to worry about that. You don't have any of those gross things. They're all nice and smooth functions. Well, I guess with the exception of in our class, we're assuming that you can just be chilling at rest and then all of a sudden be at some positive acceleration, right? That's not continuous, but we don't worry about that change. We just worry about while that acceleration is positive. Okay, so that's how we define it. So graphically, it's the slope. So if I just take some points that are nearby, right? So I can say, here is what this would be if it were a straight line, and then what's the slope of that line. Right, so I should, and as I get those points closer and closer together, that's going to become the tangent line at that point. Okay, so right, so this is a function, and this is the the variable that it depends on. Right, so when we move this to physics, we normally think about an independent variable and then a dependent variable that depends on it, right? More than a function. So if we have x as a function of time, right? So trying to think. In this class, I think for derivatives they'll always be with respect to time, right? And time is sort of the ultimate independent variable. We can't do anything to change the time. right? So if we have position as a function of time, so like to pick an example that we are working on, you know, the position with a constant negative acceleration, we get this kind of shape. So in this case, you know, so if you say what's the derivative then, so dx dt, if I do a similar thing here, so I can write this a little more simply. I could say time 1, time 2, and it's x1, x2. Right, so it's just x2 minus x1 over t2 minus t1 as these become close. So, any questions so far? So we can tell that at this, you know, if we just think of what the tangent line would be, right? So the tangent line is the line that only touches that curve once, right? So can you pass me a napkin? Right, so I can take this napkin and say, okay, how close can I bring it, right? So right there, this line of this napkin is going to give me the velocity at the time, you know, corresponding to the time or to the position where it's actually touching. So around here, it's close to that velocity. You know, if I go just a split second before, we're almost to that velocity. Where our velocity is a little bit bigger, right, because it's steeper there. And if we go a little bit past that time, it's a little bit less steep, so that means our velocity is a little less, but still positive. So as I move this around, the slope of this line is going to tell me what the velocity is. And when I get to the maximum, my tangent line is horizontal, so that's where my velocity is 0. Right? And the other way that you can think about that is, you know, just before this point, I was moving, you know, so say positive x is this direction. Just before I got to that time, I was moving this way, and just after it, I'm moving the other way. So in between, I have to go through 0. So let me do something a little bit more general before we get to the specifics that we're doing. So let me take this plot again and just make something a little bit more generic. Well, I'll erase. So I'm just going to make up some position versus time graph. And we'll try and make a sketch of what the velocity and acceleration time graphs look like. So, velocity versus time, and finally acceleration versus time. Okay, so position versus time, I'm going to do this, that. Okay, and then I'll just give us some reference point, I'll mark this in seconds. Right, so we'll say 1, 2, 3, 4, 5 seconds. I guess velocity and acceleration I need to consider, they could be negative. So 1, 2, 3, 4, 5. Okay, so at time equals 0, what's the velocity? You know, positive or negative? It's negative. And then after that is the magnitude. So is it going to be getting more negative or less negative?
Less negative.
And how do we know that?
The curve's approaching, it's getting flatter.
It's getting flatter, right? So I know I'm going somewhere, I start some negative value, and then I get less negative, and then eventually I get to zero velocity where I reach the minimum here. Right, so I'm just going to pick. So now I don't know if these are straight lines or what, right? So it's kind of, it's probably something, not quite straight. So at around time t equals 2, that's where I get to 0. So I start negative and get somewhat less negative. And then, if I'm going through 0, my velocity must be positive, right? So I get positive, I get more positive as it gets steeper, and then eventually I get to, so positive, more positive as it gets steeper, then it levels off, so I'm going to get less positive, and then eventually get to 0 again there, around time, just before time equals 4 seconds, so 2, 3, 4. So I'm going to have to go something like that. Right, so I don't know exactly the shape, I'm just sketching. And then negative slope again, so I go to negative velocity again, and sometime past t equals 5, I'm going to go positive again. So then for acceleration, I just do the same thing from my velocity curve. So I've got 1, 2, 3, 4, 5 seconds. So my velocity is negative, but it's getting less negative, so my acceleration should start out positive. And then where does my acceleration get to 0?
3 seconds.
Somewhere, 3-ish seconds. And then it gets to 0 again somewhere before 5. So so it starts out positive, gets to 0 about here, goes negative until about 5 seconds, maybe a little bit before 5, right? So something like this and this. So now there's another way where I can, and we talked about this a little bit in class on Wednesday, I think, where we can look at the position versus time graph and sort of go straight to the acceleration and know whether it's positive or negative. You remember what that test was?
Second derivative.
So it's the second derivative, so how can I tell if the second derivative of a function is positive or negative?
Concave up is positive.
Right, so when it's concave up, that means that the second derivative is positive. And when it's concave down, then the second derivative is negative. Now, it's a little bit hard to tell. Well, in this plot, it'd be very hard to tell exactly where it switches from being concave up to being concave down in between. But I know somewhere in this region it's positive, and somewhere in this region the acceleration is negative. So somewhere in between it goes to 0. It's hard to pinpoint by my drawing. But, a lot of cases that we'll deal with are like the case that we had on Wednesday, where it was concave down the whole way. So that can be a helpful shortcut, but you can always just take what you start with and take one derivative, plot it, and then plot the second one, like we did. questions so far? Yeah.
So if we assume for the velocity graph, from 0 to 2 seconds, if it was a linear line, would the constant be like a flat?
Right. So if if this were a linear line, then the acceleration would have to be flat until it got to here.
Okay.
Right. But that would imply something discontinuous, something that's so that would mean that rather than this being smooth, it would have like some sort of bend in it, right? Which maybe it does by how I've drawn it, but. Right, so if these were all, like, let's, Anyway, so I kind of tried to draw that curved so that I wouldn't have to do that. And I think we'll talk about that when we start with acceleration and go the other way when we do intervals. Question? Okay. So now the other question is a refresher on how to actually calculate derivatives. So the main thing in this class that, and I can't remember if, other than graphically, if we're going to do any sorts of integrals, or sorry, derivatives that aren't like this, but polynomials, right? So derivative of polynomials powers. Right, so a polynomial is something where you have, so we'll work with t as our variable, right, because that's what we're mostly dealing with. So you have, terms that are t to some power, right? So, you might have, so x of t, like if somebody gave you this 4t cubed plus 8t squared plus 6t plus 5. So with derivatives and with integrals, you have, if you have things added together, you can do them each separately. Right, so this just means that we have to do four different derivatives. Right, so the rule is that dx dt, well, so if x is equal to some constant times t to the n, then dx dt, basically you bring down that n, so you get n times whatever constant's in front, t to the n minus 1. So every time you take a derivative, you go down 1 power overall. So we won't worry about where that rule comes from. That's for your calculus teacher. So in this case, it's all just lined up for us, right? So we've got constants in front, so bring a 3 down, I get 12 t squared. Bring a 2 down, I get 16 t here. So t to the 1, I bring down a 1, that does nothing. And then I go to t to the 0, which is 1. Right? So I kill that one off. And then constant has no dependence on time, so it just goes away. So this would be v of t, right, if that's a position. And then we could calculate the acceleration. this gives us 24t plus 16. So as we can see, if the position has a t cubed, then that means that our acceleration is not constant, right? It depends on time. So in this case, we wouldn't be able to use any of those kinematic equations because those all assume constant acceleration. So as an aside, the derivative, or the rate of change of the acceleration is called the jerk. So if we take the derivative of this, we get j of t, and that's 24. Right, so I'm not putting units with any of these. So I'm being a little sloppy, but we're more worried about the math right now. Right, so in this case, you know, we can see, so x of t has this constant value. Well, so when t equals 0, what does x equal to? It's just 5, right? So that would be like our starting position, right? Our x sub 0. So of course that can't affect the velocity, right? How fast you're going doesn't depend on where you define your 0. So that's why it goes away when we take the derivative. And then this then would represent a starting velocity. We have a starting acceleration and then a constant jerk that changes all those things. So kind of a fun exercise that I did with some students last year was to get the equations, so sort of the kinematic equations for a constant jerk instead of a constant acceleration. So we did the train problem, assuming a constant jerk instead of a constant acceleration.
What are the units?
For jerk, that would have units of, well, every time, so we can look at this and say, okay, whatever, we can treat it like a fraction, units-wise, right? So meters per second, right, it becomes a velocity. So meters per second squared, so what would jerk be? Yep. And actually, jerk is pretty important in engineering because, I mean, it's called that because that's what you feel, right? When your acceleration, you know, if somebody stomps on the gas pedal, you feel jerked back into your seat. So, you know, we did the problem assuming, okay, people only like a constant acceleration, but or a maximum acceleration of whatever. But really, you got to keep the jerk under this number, otherwise, it'll feel too jerky. So, it's an interesting exercise. So any questions about this? Yeah, so you know, if we think about plots, right, if I plot, okay, I'm going to do a different sort of plot. So I'll do an x plot that looks like this. So this is x versus time. Right, so if this is quadratic, you know, so the highest power is t squared. What do we know about the velocity versus time graph?
Highest term would be x.
Sorry?
Highest term would be x.
Or t, right? T is our variable here, right? So its highest term would be t, so what shape does it have?
Linear.
Linear, right? And then the acceleration, what sort of shape would that have? Would be a constant, right? So this is what we're familiar with here. So here, the velocity starts out negative and becomes positive. So the acceleration as a function of time, should it be a positive constant or a negative constant?
Positive.
Positive constant, right? Because the slope of the velocity curve is positive. The x plot is concave up. So A is constant. So those are kind of the main things, right? Understanding that the derivative is how something changes with respect to time, right? So in our case, how your position changes with respect to time is called velocity, and how your velocity changes with respect to time is called acceleration, right? So those three have that derivative relationship, and then being able to identify graphically, at least whether the derivatives are positive or negative is important. And then finally, relating, in our case, where we are going to have this, usually a quadratic position plot, knowing the shapes of the velocity and acceleration. All right, any questions, or are we ready for integrals? Okay. So in terms of computing them, the integrals are just doing derivatives backward, right? So, in calculus you hear it called the antiderivative, right? Because the integral, and this is the fundamental theorem of calculus, it's that if you know the antiderivative of the function, then evaluating that tells you the area under the curve of the function. So that's the magic, right? That's sort of, it's not magic, right? It's real. But that's the key, right? So you can define an integral and say this is how it happens. It's this area under the curve, without knowing how to calculate it. But you know how to calculate it because the fundamental theorem of calculus says find the antiderivative and evaluate that. So integrals. So trying to do this in parallel to derivatives, but I forgot what I started with. Graphically, I guess, drawing pictures. So so let's, instead of starting at what I think of as the top, right? Because when you take derivatives, you go down. When you take integrals, you go up. I don't know. That's how I think of it. Because you're going down in the power, I guess, in terms of polynomials. I never really realized that might not make sense to everybody. Have you ever thought of it, so like, a low frequency sound? Across cultures, most people call it low. And then a high frequency sound, we call it high. But we didn't know it was frequency, but most cultures have that terminology that we associate, tubas with, like, down here, and flutes are up here. I don't know why. So that doesn't have anything to do with anything other than that I said that we're starting from the bottom with integrals and working out. So acceleration as a function.
I was confused at how that connected.
Yeah. It's 4:30 on Friday, so my logical connection might be a little looser. Have you ever noticed, like, when you're falling asleep, that's how you can kind of tell that you're falling asleep, because you can't, like, retrace your thoughts. But then if you think about that, then that usually wakes you up. And so, anyway. But I've heard that that's the first step in learning how to lucid dream, where you can control your dreams, is being very aware as you fall asleep. Okay, so if we want to stick to the things that we're going to cover in this class, which is constant accelerations, okay, I could just draw a flat line. But I think one thing where people get a little bit mixed up is, in this class, is we can do constant in pieces, right? So, you know, whether you're talking about the basketball player jumping problem, right? In that case, it's a constant acceleration because we can only know about the acceleration like once the player's left the ground, right? As they're bending their knees, how they actually spring off the ground, that's not what we're interested in. How they, you know, stop when they land on the ground, it's not what we're interested in. Same thing with the train, right? We have it stopped, then it has a positive acceleration, then it has a negative acceleration, then it's stopped again, right? So we might have a case where the acceleration is like that, and then positive, and then negative. So I'm trying to line these up, right? So really in real life we can't do this, but this is an assumption that we have to make, and it's usually pretty good for the types of problems we're interested in. Okay, so for integrals I just want to do this, right? So when I integrate, it's the area under the curve, right? And so like part of the reason why I'm doing the programming is because it doesn't matter how you add up those changes, right? We did it, you know, the computer just made a bunch of, you know, little steps. We can do calculus. So what's the area under this curve? What's the area between this line and 0? 0. So what should the velocity be?
0.
Oh good, you fell into my trap. Remember when you integrate, what else do you get besides the answer to besides the antiderivative?
Initial velocity.
You get a constant, you get your plus c. So there's no way to know from this graph alone how fast, you know, what the velocity of the object is at time equals 0. All we know is that the velocity stays the same. Right, so so maybe it's moving in a negative direction for the first part. Now in a problem, that's very important information, right? Like if I want to say like how far does a train go after accelerating for this amount, you have to be told how fast it's moving before that time starts. Okay, so that's going to be, you know, when we integrate that, we just get a constant. So how about for this section? So I have a positive acceleration. What does the velocity look like? Positive slope. And since this is a constant, the slope's going to be constant, so it'll be linear. And again, we don't know, since we don't know what the starting velocity is, we can't tell, like, is this going to cross 0? Is it not? That's information that's not provided by just this plot. So I'll assume it crosses 0. Okay, and then how about the last section where we have a negative acceleration? What does the velocity plot look like? Downward sloping line. So the slope of that is going to depend on whether these are the same number or not. I'll just kind of generically do that. So how would I be able to tell just from this plot? So let's say that these are, so this is, you know, whatever, plus 6 meters per second squared. And this one is minus 6 meters per second squared. What would have to be true in order for this velocity to get back to where it started?
Can you rephrase that?
Yes, so started out at some velocity. So let's assume that we get back here at this point. This velocity is the same as where you started. Right, so you started out going negative 5 meters per second or whatever. And at the end you're going negative 5 meters per second again. What would have to be true about the motion in order for that to happen?
an acceleration have to like decrease to get to that point?
Yeah, well, it did. It's definitely negative.
The same amount.
The same amount of what?
Like you have to, the acceleration, you accelerate for the same amount of time that you decelerate?
Yes. So, I don't want...
Negative
Yeah.
acceleration.
Right, because here this would be slowing down, and then this part you're speeding up because you go to 0 and then you get to a bigger negative velocity. Right, but, so if these are the same number, I'd have to do the positive acceleration, right? So let's just say, like, I'd have to step on the gas for the same amount of times that I'm stepping on the brakes. What if these weren't the same number? How would I be able to graphically figure out that I got back to my starting velocity? What would the integral of acceleration versus time have to be? Well, it is velocity, and it's the change in velocity, so it would have to be 0. So the integral is an area under the curve, right? So, but this is positive, and this is, we have to treat this. I mean, I know in like real life, there's no such thing as a negative area, right? You can't have like a 600 square foot house that has a negative 50 square foot addition to it. I don't know what that means. But in terms of the integral, that's what, when you're below here, that's a negative value. So if we get back to where we started, that means, in terms of velocity, that means this area cancels out that area. That's okay. Does that make sense? And then, so if this area were bigger than that area, and I'm not talking in terms of positive or negative, right? But just, say this was +8 and this is +7. What does that mean about the final velocity? Is it greater or less than what you started with? Greater. And vice versa if that were a bigger area. Okay, so then the last thing that we can do is plot the position versus time. So, what should our starting position be? We don't know, right? So that would have to be something that's given in the problem. Now, I messed around with the velocity. I'll just say that we're starting at x = 0 because position is the one that we can more arbitrarily choose, right? Velocity is sort of an absolute thing in our case. So say we start out at x = 0. So then during this first section, which way would we move? Or what should the x plot look like?
Should we constantly down?
What do you mean by constantly? Constantly down.
Like going the negative?
Going in the negative with a constant slope, right? So we have like that, right? Because when we take, just like when these constants got integrated, they became lines. This constant, when it integrates, becomes a line with a slope. And since this is negative, it means we're going toward the negative direction, whatever that is. Okay, so we got our first section there. And then now we've got, we reach a section with a velocity that's linearly increasing. So what sort of shape should we have?
Quadratic.
Right, so it should be quadratic, and it should be concave up, right? Because our position is going to,
It's going to be down. Wait.
well,
Slope it.
at some point, so where's the minimum position? Where's the minimum of the position? Is it here?
Yes.
Where do we turn? At what point on this graph do we turn around? So I'm moving in the negative direction, right? The velocity here is still negative, right? So I'm still moving down.
At the 0 point.
So I turn around when this point equals 0, right? So this is gonna still be decreasing, but now it's gonna become a parabola. So I'm gonna mark these points here. So special points. So if we call this T1, so here's T1 on there. So we don't turn around until we reach T2. Right, so T2. So here I'm drawing like the bottom of a parabola. And then who knows when it's kind of hard to tell from this. Like if we really had numbers here, we'd be able to tell when we crossed x equals 0. But from here, it's a little hard to tell. Right, so anyway, don't know where I'm going to cross t equals 0, and then t3. So I'm just going to go up. So maybe I never cross t equals 0. So what happens at t3? Do I turn around?
You're at like a peak.
A peak of what?
It's the peak of like the parabola segment.
Well, even after I get past t3, my velocity is still positive. So it switches from being a positive acceleration to a negative acceleration, right? But if I'm, so here's where I'm hitting the gas. Here's where I'm hitting the brakes, right? So here's, I start hitting the brakes. I don't go backward when I hit the brakes, right? My velocity becomes less positive, right? So in math terms, this would be an inflection point, if you remember what that is. I'm going from being concave up to being concave down, right? So this sort of turns over. And I don't reach my maximum position until my velocity is equal to 0, so t4, wherever that is. Right, so I don't reach a maximum until I get there. And then my velocity becomes negative, so that's where I turn around. So here's where I go from concave up to concave down, right? So you can kind of see going, it's this SCurve-ish thing. Right, so I think that's, in terms of integrals, that's one of the trickiest points, right? Because when you have a velocity that goes from positive to negative, you're like, okay, a positive slope to a negative slope, you're like turning around. Not true. Velocity is still positive, so you still move in the positive direction. So you're still moving forward, so you gotta think of that as a positive velocity. So the turning around points happen there and there. So this plot says that I start out going backward, and then eventually I go backward less fast until I start going forward, and then I go forward less fast until I start going backward again. So how can I tell? Okay, so clearly if I'm trying to see, so my question from this plot is, do I ever get back to my starting point? Here I kind of assumed that I did, but again, we're working without numbers. But how would I tell from this plot if I ever get back to where I started again?
The integral, the total,
Mm-hmm.
total area for each part.
Right. So this area, which is how far I move backward, and this area, which is how far I move forward. Right, so if by this point I exactly get back to starting point, what would these areas be? Equal. Right, so if this area is not at least as big as that area, I never get back to the starting point before I turn back around again. Okay, so so any questions about like the graphical situation?
Can you look at the area for either the velocity or the acceleration?
Just velocity, right? Because the area for the acceleration tells me how much what has changed. The velocity. And the area for the velocity tells me how much the position has changed. So I can't tell at all. There's no like second integral test like there is with the second derivative test because I don't know what this constant is. Right, so the second derivative test, meaning, is it concave up or concave down, tells me about the acceleration. There's no way I can look at the acceleration and say, like, where did I get? Because I need that extra information. I need the initial velocity. And that's nowhere on this plot. Now, once I've assumed some initial velocity, then I can get there. So,
Wait, how would you get the initial velocity other than assumption?
no way. There's no way to know. From the accelerator, if I'm given the acceleration plot, there's no way to know the initial velocity. I have to be told. So that's why, I mean, when that comes in, like when you're doing your integrals in calculus class and you put that plus c, that's that, I don't know what the initial value of the next higher, I'm using that metaphor again, but the next, what the antiderivative looks like. I need to be told that initial condition. So, basically, so if I have the position function, or plot, or whatever, I can, in principle, know everything by taking derivatives. But if I start with the acceleration, I don't know everything. I need to be told an initial velocity and an initial position. So if you take, have any of you taken differential equations class? So, I mean, in a differential equation, you're basically given some information about a derivative or a second derivative, right? So if you have, like if I'm given the velocity, that's a first derivative. I just need to be told the initial position. But if I'm given the acceleration, in order to know everything, I got to know two initial conditions: the initial velocity and the initial position. So that's just always. So now we did a little bit when we talked about the programming example of knowing how the integral of a constant becomes something times becomes linear, right? Because if I'm saying, okay, let me take away this part and just look at this. If I have a constant and I say how much area is 1 second, and I get some number, and then I say, okay, let's do it for 2 seconds. What happens to the area? It doubles, right? So whatever this is, so that means as I increase t, the area goes up linearly, right? And then we get this velocity curve, right? So now it's not quite so smooth, or smooth is a bad word to use. It's not quite so simple, right? But it became a triangle. And we said, well, how tall is this triangle? Well, it depends on what, it was, if I added up the area, for t time, then this is, the velocity after some amount of time t becomes at.
Can you repeat that?
So if I accelerate at a constant value for t seconds,
Okay.
or t amount of time, right? That's what I plot here. So this here is the change in velocity is at. Right? So if I started at v equals 0, then I just have this triangle whose base is t and whose height is at. Right? So the area is 1/2 a t squared. 1/2 base times height. So that means that after, if I start at x equals 0, well, after t seconds, I should be at 1/2 a t squared, so that plot over time is going to be a parabola. And if I wanted to go, if this wasn't position, if this was something else, and I wanted to take another integral, then I can't do any geometry anymore. I really do need calculus. Because I know the formula for this area, but that's not geometry. You're doing calculus now for real. So this is, if I wanted to do that without thinking about areas, this is kind of a clever trick to connect it to something else that you know about, namely triangles. But if I want to do this antiderivative, I just need to remember the rule for derivatives and just do it backwards, right? So let me see if I can remember this in general, right? So how do I write this? Integral of f of t dt. Well, no, I don't want to write it that generally. This is impossible. Okay. I wanted to do some constant times t to some power, right? So when I took the derivative, the power decreased by 1. So when I take the integral, the power has to increase by 1. Right? So a constant always comes through. I'm going to have t to the n plus 1. But when I take the derivative of this, I better get what I started with. But if I did that, I get an extra factor of n plus 1. So I need to divide by n plus 1. I know that's kind of some double talk, right? But, so let's do a specific example, 8t squared. Right, so integral of 8t squared dt. Well, I'm going to get an 8, because that stays there. I'm going to get a t cubed. But if I said this was the answer, right, what happens if I take the derivative of this? Do I get 8t squared? No, I get 24t squared. So I need to divide by 3. So now when I take the derivative of this, I'll get 8t squared. So that's how I think of it. I add the extra power and then I say, okay, when I bring that down, what's the extra factor that I don't want? But this is a general formula that says basically that. And that's basically what I have to say about calculus for this semester. We'll do some other integrals in class that aren't functions of time, but that'll be later down the road and I won't assume as much. So, for instance, like work is you integrate a force over time. Force over a distance. So that's a little bit of a different sort of thing, but so I think this took, man,